Right. You're welcome, all of you, to our channel once again. Today we are going to look at the effect of temperature. So chemical kinetics lesson 6. We're going to look at the effect of temperature on rate of reaction. Now, when we talk about temperature, you just need to know that when molecules are heated, right? When you heat molecules, what they do, they gain kinetic energy, or their kinetic energy increases. And a larger fraction of them will move or will have sufficient energy to overcome the activation barrier that is EA, and thus the rate of reaction will increase. In addition to this, also at high temperatures or at higher temperatures, when you have heated molecules or ions, at higher temperatures, the ions, the reacting ions or molecules, they have more energy, what we call the kinetic energy. They have more energy, all right? And that energy, they have more energy and they are moving, okay? The ions or molecules, let me say, of the reactants have more energy moving with greater average force or greater average velocity, moving with greater average velocity, all right? And they collide more frequently and collide more frequently. And as they collide more frequently, they do so with more force. And we shall realize that the increased number of collisions the increased collision frequency will result in a higher rate of reaction. So at higher temperatures, the ions or molecules of the reactants, they have more energy, that is the kinetic energy, moving with a greater average velocity. And as they move, those particles will be colliding more frequently with each other, and they do so with more force. So the increased collision frequency will result into a higher rate of reaction. Very, very interesting. And from this case, we shall look at this. Basically, we are going to look at the Arrhenius dependence. We're going to look at Maxwell-Boltzmann's and others. But I want you to know that the increased temperature, one increase in temperature, doesn't affect the activation energy of the reactants, but instead it just increases the number of molecules possessing the activation energy. And that is what exactly I'm saying, that the kinetic energy increases and a larger fraction of them will have sufficient energy. It doesn't mean that the activation energy has increased. No, a larger number of molecules have a higher activation energy. Now, let's first look at the Maxwell-Boltzmann's distribution of molecular energy. Distribution of molecular energy. Now, this pair of gentlemen stated that, okay, these people stated that rate of reaction doubles, the rate of reaction doubles for every 10 degrees Celsius or 10 Kelvin rise in temperature. For every rise by 10 degrees Celsius or 10 Kelvins in temperature, the rate of reaction doubles. Basically, that is how they stated. And then they came up with a plot of the number of molecules that possess that energy E with the or against molecular energy. And that is the plot that I want us to discuss. Then from there, we go to the relationship between the rate constant and temperature. Okay, so let's look at that plot. I'll call it a plot of fluxion of number of molecules with energy, number of molecules with energy E against molecular energy. In other words, we are plotting the number of molecules that possess the energy and then that very energy. So they came up with this plot, and here we are having a number of molecules. When you're plotting, you have to write the whole word. Number of molecules with energy E against molecular energy. So that molecular energy is what we call E. For the case of this one, we have that, and then this. So we have these two curves, and that is what we are going to explain. This is T1. At this point, we have T1, and at this point, we have T2. At this point, we are having activation energy EA, and let me shade this like this. I shade this region maybe like this. Now, you're going to realize that at lower temperature, T1, I'm calling T1 at a lower temperature because if you, we don't have access label the temperature, but I'm calling it a lower temperature, and then T2 at a higher temperature. Now, the interpretation would be like at lower temperature, T1, a very large fraction, because you see the number of molecules are too many. A very large fraction of molecules, they have energy close to the average energy. So only a very small fraction of molecules, with only a very small fraction of molecules having very high or very low energies. However, at a higher temperature T2, there is a wide range of molecules, all right? There is a wide range of molecules. So a proportion of molecules with energy greater than or equal to a greater increasing likelihood of successive collision, which increases the rate of reaction. So this question can come in a way that they can ask you with the aid of a labeled diagram, or with the explain with the help of Maxwell distribution diagram, why the rate of some reactions approximately doubles when temperature is increased by 10 degrees around the room temperature. So the moment you increase T1 by 10 degrees to T2, just need to know that at T1, a very large fraction of molecules have energy close to the average energy. So only a small fraction of molecules will be having a high or a low energy, or very high or very low energies. However, at T2, as we increase to T2, there is a wide range of molecular energies, okay? Proportion of those molecules with very, there is at T2, there's a wide range of molecular energies. There's a proportion of molecules with energy greater than or equal to the average energy, thus increasing a chance of successive collisions. So at T2, there is an increased chance of collisions, meaning that the moment you increase the temperature from T1 to T2, you expect a lot of collisions of the particles, increasing the rate of reaction. So even if the question is explain the rate of reaction when T1 is increased by T2, explain what happens to the rate of reaction. The first thing is to first tell us that the rate of reaction will increase, because an increase in temperature will increase the kinetic energy of the reacting particles or ions or molecules, which results into a higher frequency of collisions. When the frequency of collisions increases, the rate of reaction also increases. So in this particular case, we shall have our T2 greater than T1. It's a very common question whereby they can ask you the effect of increase in temperature. All right, now from this, we are going to look at the relationship between the rate constant and temperature. Now, if we were to look at the relationship between the rate constant and temperature, we do this specifically by looking at the Arrhenius equation, because it's the Arrhenius equation that relates the magnitude, the rate of constant, and then the temperature. Now, this man called Arrhenius, he noticed that the dependency of reactant, the dependence of reaction, excuse me, this man Arrhenius, or the Arrhenius himself, noticed that the dependence of reaction rate constant K on temperature varies as this. You noticed that the rate constant varies as that. So this is called the Arrhenius equation. When I talk about Arrhenius, one may be interested to name their children Arrhenius. So this is the spelling, A-R-R-H-E-N-I-U-S. So this is the Arrhenius equation. So this is the Arrhenius equation that will give us the rest of the equalities that we need. But we've seen that K is the rate constant. This A stands for the frequency factor. Some books call it Arrhenius factor. While some books call it the pre-exponential factor. What else to define? R is the molar gas constant. And specifically, we shall use 8.314 case of calculations. EA, that is the activation energy. So the frequency factor, okay, is obtained by the experiment, okay? And we relate it to the frequency of collisions and orientation of the reacting molecules, all right? So in this expression, from this equation one, let me call it equation one, or the Arrhenius equation, when you take natural logarithm both sides, if you take natural logarithm both sides, it would mean that you have you'll have ln K, natural logarithm is ln, so you'll have ln K is equals to ln A, all right, minus, it will be minus EA out of RT. That is by taking natural logarithm both sides. Now, this one, after having taken the natural logarithm either sides, we are going to find that this expression, okay, this expression is going to end up becoming 2.303 log 10 of K. If we are to write ln in terms of log 10, so we're introducing a factor 2.303 log 10 of K. is equals to 2.303 log 10 of A. That is, we have eliminated ln, because that ln is the same as 2.303 log 10. Then minus EA out of RT. So if I'm to put it in form of an equation, I'm going to have if I make this one the subject, log 10 of K. So my log 10 of K is going to be equal to okay, you can check, you can work on this equation. All right, you can work on this equation very, very, very carefully, because this EA over RT is the same as EA over R, then times 1 over T. They are the same. So I can as well split it from here so that I get minus EA over 2.303 R, then 1 over T, then of course plus log 10 of A. One may wonder where this one has gone, because if I make log 10K the subject, it means that I divided by 2.303 either sides, here, here, and here. So here it went, and here it also went. So I'm left with it here on EA over RT. So this equation, by looking at this equation, it is in the form Y is equals to, this is M, okay, this is the gradient M, and this is X, and this is plus C. So on Y-axis, if we plot log 10 of K, all right, and on this one will be our gradient, and 1 over T will be on X-axis, and log 10 of K will be our intercept, our y-intercept. So in short, what I'm trying to drive you to is that when you plot log 10 of K against 1 over T, you plot this, a plot of log 10 over K, log 10 of K against 1 over T. You see the gradient is negative, and therefore we shall have it as negative line. So you can plot, and maybe your graph appears like that. So when your graph appears like that, by extrapolating here, we shall have our intercept, which is log 10 of A. You can easily determine that A from the graph. Then remember, we plotted the log 10 of K against 1 over T. Okay, now this one can give you the slope. Which slope we said is equal to negative EA out of 2.303 R. So the slope can get you activation energy. The graph itself can give you the value of A. That's it can give you, because R is a constant. So by having the slope, if you ask to get activation energy, you can easily substitute and you get it. You can easily get the value of A, because if at this point maybe you have gotten a point and maybe it is M, it means that M is equals to log 10 of A. So if you need that that Arrhenius factor or the pre-exponential factor, it means that your A can be equaling to, this is the base, so it will be 10 to the power m if you eliminate logarithm. Okay, so this is the base, this is the power, and this is the number. Okay, so the graph can give you whatever you want. Before we look at the examples, I want to first relate it to, I want to first come up with some other, from some other equation. And I'm going to say, if we suppose a reaction at T1, if we suppose that the rate constant is K1, and at T2, the rate constant is K2, where we shall assume that T2 is greater than T1, and thus K2 is greater than K1. So we are trying to derive an expression that will look at the expression generally, an expression that we shall be using. So it means that log to base 10 of K2 from the other previous derived thing is going to be equal to negative EA out of 2.303 R 1 over T2 plus log 10 of A. You call this one equation 1. Then for equation 2, log 10 of K1 is equals to EA negative out of 2.303 R 1 over T1 plus log 10 of A. You call this one equation 2. So if you subtract 1 and 2, you'll have log 10K2 minus log 10K1. I'm getting this minus this. It will be equaling to, of course, this one will go. So we are going to have, both of them have this. It has this, they have the same thing, so I can factorize it out. But since you're subtracting, it will be this minus negative that. So it will be positive. In this case, we shall have it as positive. So it will be EA, all right? It will be EA out of 2.303 R, then 1 over T1 minus 1 over T2. All right, 1 over T1 minus 1 over T2. So this one here, this expression, we shall be using it to determine some of the stuffs. And here you can see, since you're subtracting numbers with the same logarithm, you can easily see that you can put them under the same base and you say K2 over K1. You can divide, and this is going to be going to EA over 2.303 R. Here the LCM, so the whole thing will be T2 minus T1 out of T1, T2. The LCM is T1, T2, so the upper thing is going to become this. So this equation can be used to calculate most of the questions that can come on this. And alternatively, one can write this one as ln K2 over K1 is equals to EA, right, out of 2.303 R of T1 minus T2 out of T2 T1. One can use ln, one can use log, okay, or one can say log K1 over K2 is equals to EA. Here, if it is to be T1 minus T2, then this one has to be log K1 over K2, so that you have T1 minus T2. But if it is K2 over K1, now it is the same as that. So even if I don't complete it, but you can as well have this, you can as well have this, depending on the values that will be given. So, for example, if we do like one question on that, let's get a calculation. The activation energy of a certain reaction is 50 kilojoules per mole. What is the effect on the rate? Effect on the rate constant of increasing the temperature by 10 kelvins around room temperature, which is assumed to be 15 degrees Celsius. To work out the solution of this, our T1 is 15, which we assumed to be the room temperature. So we shall add 273 so that we convert it to kelvins, and it will be 288 kelvins. Then our T2 will be, we shall add 10 kelvins because they are saying increasing the temperature by 10 kelvins. So we shall have 288. We add 10 kelvins and it will become 298 kelvins. Now, after getting all this, from the formula log K2 over K1 is equals to activation energy out of 2.303 R T2 minus T1 over T2 T1. It would mean that our log K2 over K1 substitute activation energy was given as 50 kilojoules per mole. So if we make it joules per mole, it will be 5,000. Okay, it is a kilojoule. So if you make them, you put them in joules, we shall multiply by 1,000, then over 2.303 times R, the molar gas constant, 8.314, into T2. Temperature 2 is 298 minus temperature 1, it is 288. Everything out of T2, that is 298, times T1, which is 288. Now, log K2 over K1 by putting on the calculator. It is going to come up with 0.30426871. But I'm interested in K2 over K1. So K2 over K1 is going to be equal to the antilog or the log inverse of 0.30426871. And this is going to give you 2.0149. Implying that our K2 over K1, the fraction, is approximately equal to 2. The question is, what is the effect on the rate constant of increasing temperature? So this is the fraction of the rate constant. Therefore, we shall say the final rate is twice the initial rate, because the ratio is 2, or the ratio is 2. So we shall say that therefore the rate, or the final rate, is twice the initial rate. Very well, very well, very well. So I'm going to give a question which is graphical, and then I see how we can work on it. So it is about the variation of rate constant with temperature for decomposition of hydrogen iodide gas to hydrogen gas and iodine gas is given below. So we have temperature in kelvins, and we have the rate constant. So temperature, we have 55. Here we have 3.52 times 10 power negative 7. Then here we have here we are having 575. Then here we are having 1.22 exponent negative 6. Here we have 645. Then here we have 8.59 exponent negative 5. Then here we have 700, 1.16 times 10 to the power negative 3. Then here we have 781, and this is 3.95 times 10 to the power negative 2. So that is the table. It shows the variation of rate constant with temperature. The first part wants you to plot a graph of 1/T against the rate constant, against the ln of rate constant. 2, use the graph to determine the activation energy. This question is very easy because you first fetch 3 marks by working on this. So meaning that we have to draw a new table indicating these values, 1/T and ln K. So we are going to have 1/T and ln K. Allow me just put the values of only this. So for one, when we take 1/T of this, 1/555 on a calculator, it is going to give you 1.80 times 10 to the power negative 3. When you put 1 over that, it is going to give you 1.74 times 10 to the power negative 3, sorry. When you put this, it is going to 1 over that, it is going to give you 1.55 times 10 to the power negative 3. And when you put 1/700, it is going to give you 1.43 times 10 to the power negative 3. Finally, when you put 1/781, it's going to give you 1.28 times 10 to the power negative 3. Ln K, when you take ln of this constant on a calculator, you press ln of this, it's going to give you negative 14.860. When you take ln of this, it's going to give you negative 13.617. When you take ln of this, it is going to give you negative 9.362. When you take ln of this, it is going to give you negative 6.3.759. Then when you take ln of this, it is going to give you negative 3.231. So by plotting these two, since they want me to plot graph of 1/T against ln K. Now, since they all have this power, okay, since they all have that power, same power negative 3, so I can, and the ln is negative, so I will have my graph like this. I'll have my graph like this. So you choose the appropriate scale, and this one is the task of any viewer to draw this graph. So of course here we shall have 1/T, meaning the units will be per Kelvin. Since the units here was Kelvin, when you take 1/T, it will be per Kelvin, and you can start from 0 maybe. Since you have 1.2 up to 1.8, you can say, or you can multiply this times 10 power negative 3, and you take it from exponential to the real values, or you can deal with them the way they are, and then you say 1/T, then but you're multiplying 10 to the power negative 3 generally, and then there you can start from 0. You can start from maybe 1.0 here, Okay, you go to 1.1, 1.2, 1.3. All right, you can continue like that. All right, you can continue like that. 1.1, 1, or you can use 1.2, 1.4, 1.6, 1.8, whichever scale. 1.2, 1.3, 1.4, 1.5, 1.6. If you can use 1.0, 1.2, 1.4, 1.6, 1.8, 2.0, because you have already catered for that exponent. Then for this case here, you can, since you have from -3 up to 14, you can use a factor of 2. You can start from 0 here. The same, you can start from 0 on this axis. Then you say -2, -4, -6, -8, up to when you come to maybe -14 or 16, something like that. So on plotting your graph, you're going to find your graph like this. If they needed the Arrhenius factor, we say that you extrapolate, and when you extrapolate, only that they didn't need it, when you extrapolate, say that here is log 10 of A, but they don't need it. So they just wanted you to plot, and we told you from the previous videos that when we are plotting, you dot and circle, you dot and circle, you dot and circle, you dot and circle. So every viewer is tasked to do the plotting. So this is linear K. The moment you take the natural logarithm of anything, you will not have, or it doesn't have, the units. So from this, they want you to determine the activation energy. But remember, we say that the slope, is equals to negative EA over R from the previous derivation. So it means that you first get the slope. All right, you need to first determine the slope of this line, and the slope has to be negative. Okay, so you will determine the slope. After determining the slope, you equate it to this expression. Okay, so slope is going to be equaling to change in ln K out of change in 1 over T. So you're going to draw a slope triangle, get different values, and you get the slope. After getting the slope, that slope, you're going to work it out with this, because you already know what R is. R is 8.314. So you're going to say the slope you've gotten, maybe let me assume that the slope is 22,000 negative. It's going to be equaling to negative EA out of R, which is 8.314. So by cross multiplying, you'll get your EA as 22,000. That is what I got from my graph, but I want you to try and see if you get the same. EA is the same as 18290.8, but this is joules per mole. So if you had to put it in kilojoules per mole, it's going to become 18.2908 kilojoules per mole. So that is a task for every viewer to come up with that graph. Okay, to come up with that graph. So I'm giving you still an assignment to plot your own graph. I'm giving you the assignment to plot your own graph, and you see. But you have to follow the basics that I've given. The rate constant for decomposition of hydrogen iodide to hydrogen gas and iodine gas follows the following temperature dependence. Then here we have temperature in kelvins. So we shall have 3.16 times 10 power negative 6. This is 550. Here we shall have 7.90 exponent negative 5. Shall have 625. Here we shall have 3.20 exponent negative 3. Shall have 700. And here we shall have 0.10, 830. A photograph of 1/t against ln K. Then B, from the graph, determine the pre-exponential factor value, the pre-exponential factor A, and the activation energy. We love you so much, and we promise to keep helping you go through this period of struggle. Members, subscribe and keep tuned. Thank you. Have a nice day.